Yeah, good morning. Hi. It's a great pleasure to be here and have the opportunity to speak. Huh? Louder. Sorry.
You have a microphone, just need to switch it off on. It's on your belt.
It's not amplifier.
Okay.
Did you switch it on?
It's for him, not for me. Okay. Right. So these are some topics on electron hydrodynamics. Maybe just try to stand closer. On electron hydrodynamics in graphene and other low-dimensional systems that we worked on in the past couple of years with several people who are here and also other people who are not here, students and friends. And so I'm going to start with an introduction and then get into that topic maybe by the end of today's lecture, and then continue next time. Actually connects pretty well to the previous lecture, so I should have done, should have moved that material up a bit, but it is what it is. How many people here are theorists, and who are not? Okay, good. So it's 50-50. Right, so we'll have to try to please.
One experimentalist as 10 theoreticians.
No, usually, one theorist is equal to experimentalists.
Not 10?
No, the other way. One experimentalist is equal to theorists, right? And here they are majority, right? Good. So then this will be. I'll try to do it. On equal footing for everyone, right? So hydrodynamics. I mean, you heard about it in the first lecture and in the second lecture, and the aspect of hydrodynamics that interests me is the genetics of hydrodynamics and hydrodynamic behavior, which is an orderly behavior on large scales, streams flowing and so forth, arises from chaotic behavior on a microscale. So on microscale, there are atoms that collide randomly, and there is a fast, short time on which their microscopic state is forgotten, memory is erased, and so out of that ergodic behavior on microscopic scales, there is a macroscopic orderly behavior that we're all familiar with, and that's very familiar in everyday life. And if we go to even larger scales, then it becomes very interesting, nonlinear, and start feeling like a student at a Fall College lecture or something like that. And but what we're interested in really is how to get that in the electron system, and so whether electrons can show hydrodynamic behavior if they're strongly interacting and collisions are momentum conserving. And usually they don't behave in a hydrodynamic way. Usually they dissipate momentum pretty quickly and also energy by colliding with disorder and phonons. However, in the cases when interactions are strong or disorder is weak, collisions between electrons dominate, and you can think about what's going on in terms of conserved quantities which are conserved in electron collisions, and then there is some hydrodynamic description that arises for electron transport, and that is what we're interested in, right? Experimental systems available today are, first of all, high mobility electron systems where disorder is very low and mean free paths are gigantic at zero temperature, and when you increase temperature, electrons start colliding with each other. In addition to high mobility systems, there are strongly interacting systems where disorder may not be weak, but interactions are supposed to be so strong that they overwhelm disorder even on short distances. Now, for the what's going on? Okay, so for the purpose of today, I'll focus on the high mobility systems because they're easier to understand, and one can get away with simple transport theory. As we'll see, also they are studied in a lab, and so they are this way one can connect to ongoing experiments, so that will be my topic. There is literature that we can discuss later. The idea that electrons can show hydrodynamic behavior is pretty old, and then experimental attempts to actually see hydrodynamic behavior also go back a long time. But the convincing evidence that there is indeed electron hydrodynamics in solids is fairly recent, and we'll talk about that. Right. So in two-dimensional systems, strong interactions, and graphene will be my main example. Strong interactions arise because electrons interact in 2D via electric fields that go through 3D. And because of that, electron interactions are poorly screened or virtually unscreened, and that makes scattering interaction dominate and fairly strong. In addition, graphene has a nice features that phonons are very weakly coupled to electrons, and so dissipation via phonons is weak. Also, disorder is weak. Graphene has this magic that can be easily made very clean. In addition, the crystal symmetry is such that there is no Umklapp scattering, and so we can think about collisions as momentum conserving. And so in this case, in this case, I should stand closer. In this case, the electron transport should be understood in a hydrodynamical manner by introducing some viscosity, writing down the Navier-Stokes equations, and so forth. And if this is so, how do we know that we are in a hydrodynamic regime? And if we do know we're in a hydrodynamic regime, can we have fun? Are there any interesting new collective phenomena that we can study? So those will be the two main themes of this talk. And then, speaking about graphene, in graphene we have two different kinds of electron fluids. There is a Dirac electron fluid at charge neutrality, where electrons behave as relativistic particles with linear dispersion relation, and Fermi surface is just a point. So the ground state is like Dirac vacuum for relativistic particles, neutrino or something like that. Then if you introduce carriers, dope away from Dirac point to electron side, the whole side, then you get a two-dimensional Fermi liquid. And two-dimensional Fermi liquid is another interesting case for hydrodynamics, and it can be electron type or hole type, and there is a lot of work done on both types, and Dirac fluids and Fermi liquid hydrodynamics, both interesting and studied in graphene. I'll mainly focus on Fermi liquids, and then we can discuss Dirac fluids later if anyone cares. So this is a quick summary for what Fermi liquids are. The theory of Fermi liquids is due to Landau, and all the important ideas here were introduced by Landau, who thought about how what interactions do in the Fermi liquid. But before we get to that, the free fermions, if they have some dispersion relation, let's say quadratic, like free particles, then they fill up all the states up to Fermi level. So it will look sort of like this, fluid in a glass, with all these states being momentum states filled with particles, and then above the Fermi level, the states will be empty. And that's the picture of the ground state of an electron gas due to Fermi. And if we now think about interactions, we realize that actually, it's not so simple, because electrons are so tightly packed in the metal that if you estimate interactions between nearby electrons, they will be of the same scale as Fermi energy, or even bigger. So it is a strongly any metal is a strongly interacting system, and it wasn't obvious for a long time that the Fermi liquid description will even survive approximately in the presence of interactions. However, it was understood as early as 1956 that fermion exclusion makes it simple. And the way it makes it simple is that all these states deep below the Fermi level are blocked and don't contribute to scattering. And all, because in collisions, only energy over the kT at temperature T, only energy over the kT can be passed from electron to electron. And all the states which are deeper than kT under the Fermi level are blocked by Pauli exclusion principle. And therefore, all the action is taking place at the Fermi surface within a band of states of size kT near the Fermi energy, and that's point number one. And then all these particles, lots of them in the Fermi sea, they stay away. They're just spectators. They don't participate in the action. Then the other thing that emerged in that discussion is that the excitations near the Fermi level behave, even though they're strongly interacting with other electrons and with each other, they behave as quasi-free particles, and there is a magic that arises from a combination of energy conservation and two-body scattering and fermion exclusion that blocks states in the Fermi sea from scattering, that makes the excitations near the Fermi sea, near the Fermi level, behave as free particles in a strongly interacting system, right? And that's like a cornerstone of our understanding of metals, and it will be important for what we're going to discuss. So I just wanted to review that, and I mean, different people have different take on this, but you can take a historian of physics point of view, and then there are books and books written on the relation between the concept of quasi-particles and how you gain some degree of freedom in an oppressive environment. You have to pay, you have to compromise, you have to trade your mass to effective mass, you trade your charge to effective charge, your G factor to effective G factor, and so forth. But paying that price, you can increase your lifetime, basically. You can live long.
No temperature.
That's right. I mean, so I'm not. I'm not. So this is not a. Yeah. So it sounds like a joke, but it's not a joke for two reasons. One is that there are people. I have a friend who is a historian of science who takes this very seriously and writes very interesting research on that topic. The other more relevant for us is that this is going to be highly relevant for what we're going to discuss. So we'll find ways to increase our lifetime, or quasi-particle lifetime, even beyond what Landau theory predicts. Okay. So that that's a picture from a book. If you have a quasi-particle, it differs from a particle because it's dressed like this horse in a haystack. It's dressed by other particles that form a screening cloud, and then that screening cloud, particle and screening cloud, form a compound object, which is the quasi-particle, and we can use it and from many body theory to predict all the properties of particles like mass, energy, and so forth, and lifetime, and we'll be particularly interested in the lifetime. So the Landau argument for lifetime was that if you have a particle excited at an energy epsilon above the Fermi level, then in order to scatter, it will have to excite a particle Hall excitation out of the Fermi sea, and in doing so, it will have to divide its energy between the particle Hall pair and itself. And then, if you think about phase space for doing that, and think about this picture, how you divide fixed amount of energy in two equal parts, you see that the phase space will grow as epsilon squared. For finite temperature, epsilon should be taken over the kT, and we get this, kT squared relation for particle decay rate. So the prediction is that particle lifetime will increase dramatically by going to lower temperature and will scale inversely with temperature squared, right? And decay rate will scale as T squared, right? And so this is the standard. I mean, if you now want to connect it to hydrodynamics, then the standard hierarchy of scales in Landau Fermi liquid is that there is a ballistic behavior at short length scales described by Boltzmann type of variables for quasi-particles, distribution function, and collision integral, and so forth. And the length scale for that are electron-electron collision mean-free path, which is that number, and gamma is that T square estimate from previous page. If you now go to larger length scales, then at length scales which are greater than that mean-free path, you can, quasi-particle start colliding, and all the memory about their microscopic states is erased, except for the quantities which are conserved. And those are momentum and particle density. And then at larger length scales, what is left are the conservation laws for momentum density and particle density. And you have to work with hydrodynamic variables that Grisha introduced in the morning, and write down hydrodynamic equations as conservation laws for momentum density, particle density, and proceed with that, introduce viscosity, and so on, right? So this picture is well established in 3D Fermi liquids, and we're going to discuss how it changes in 2D. And we'll see that it changes dramatically. But before we get there, I want to just review some basic things about Hydra. And so accessing hydrodynamic regime in 3D Fermi liquids is actually fairly easy. You just need a Fermi liquid like helium-3, and helium-3 was well studied, well understood, and the hydrodynamical behavior is under control. Fermi liquid theory describes everything. In Fermi liquid, in liquid helium, Fermi energy is pretty low. It's a order Kelvin, but interactions are pretty strong because helium atoms interact basically like hard balls, and because of that, as soon as temperature is below Fermi energy, you are in the right regime. And you can go as low in temperature as about 1 millikelvin, and below that temperature it becomes superconducting, and Fermi liquid is gone. But there is a wide temperature interval from millikelvin to Kelvin where hydrodynamics works very well, and one can introduce viscosity and measure it, and thermal conductivity, and do all of that. So three-dimensional Fermi liquid in the helium-3 and hydrodynamics arising from it is well understood, and the range of scales at which hydrodynamic description applies is from collision mean-free path, which is that number we just estimated. I mean, for electrons, but for helium atoms, it's similar, up to system size, right? And so that's very nice. Now, in graphene, there are interesting differences. Well, one is that Fermi energy is quite a bit higher. So Fermi energy for typical doping can be a few thousand Kelvin, and interactions are still strong. So you're from that point of view, you're as good as in helium, or even better, because temperature range is supposedly wider. However, there are momentum non-conserving processes due to disorder and due to phonons. Disorder turns out to be unimportant in graphene. In most cases, if you have a clean clean device. Phonons are more important, but electron-phonon scattering is relatively weak, and we can, yeah. Sorry, I was thinking about it. So it's relatively weak, and because of that, we can easily be in a situation, as soon as temperature is warm enough, we can be in a situation that electron-electron collisions happen faster than electron-phonon collisions. At very low temperature, collision rate with phonon scales linearly with T, and collision rate electron-electron collision scales is T squared, just like we talked about a minute ago. So at very low temperatures, it won't work. But if you go to warmer temperatures, you can beat phonons. And so when your temperature above 10 Kelvin, your electron-electron collisions indeed dominate. So yes, there is room for hydrodynamics. The range of length scales, however, is more restricted than in helium, because you have to be at length scales larger than electron-electron mean free path for electron-electron collisions to make the state chaotic. But if you go to too large length scales, then electron-phonon scattering will win again, because it will produce ohmic effects, and it will essentially make the behavior ohmic rather than hydrodynamic at scales larger than this one. And maybe just a quick remark on that. You can understand that very easily by saying that if I take hydrodynamics of classical fluid that Grisha introduced, and say that I'll write Navier-Stokes equation with some viscosity and some damping term describing ohmic behavior. So this will be an electron-phonon term. And the force acting on the fluid will be due to electric field, and I should multiply it by charge density and by electron charge. Then you see that, and we should estimate gradient as 1 over length scale. So Laplacian will be 1 over length scale squared. And then you see from this equation that when length scales are large, the momentum non-relaxing contribution dominates, and you can forget about this term. And in order to be at the length scales where momentum conservation is good, and therefore this is negligible, you want this term to be greater than that. And that requires that the length scales are smaller than in these units, they're smaller than 8 over gamma square root. Right? And so that, if you plug in numbers, will give this condition, right? So there is a range for of scales where electrons are expected to behave hydrodynamically, and experiments aim at this range of scales. So, but you see that you need to do some fine tuning. Now, in other metals, electron-phonon interaction is not always weak, and so you can quite often have a situation that before you get to the hydrodynamic regime, disorder electron-phonon coupling will kick in, and then hydrodynamics doesn't happen, right? Both in 2D and in 3D. Okay, any questions so far? Yeah.
Could you say a little bit more about why there's no Umklapp scattering in graphene?
Why there's no Umklapp? Yeah, this is because, two reasons. One is that Fermi surface in graphene is very small. It's Dirac cone, and it's filled only by 1%. I mean, the size of K Fermi is about 1% of Brillouin zone. So Umklapp scattering cannot happen within one Fermi surface, and it could only conceivably happen by scattering from one Fermi surface to another, from K to K prime. But the vector connecting K and K prime by crystal symmetry happens to be 1/3 of the Brillouin zone lattice vector. So it's not enough to have 2 particles scattering. You need 3 particles. And for 3 particles, Fermi liquid predicts T to the cube and predicts very low rate. So that's basically. Anything else? Yeah, ask me something. Yeah, just to break monotony. Grisha.
This T larger than 10K for electrons dominating of electron phonon, it somehow must be restricted from above 2. At some higher temperature it stops working. The dominance of electrons.
Well, I mean, of course, now if you go to very high temperatures, you start getting contribution of optical phonons. This is just acoustic phonons. But optical phonons in graphene are not a danger because they're at 1,000 Kelvin, 2,000 Kelvin, and so you have to go really to a few hundred Kelvin to be in trouble. But I think what's implied is, why do we care about phonons at all if all you need is to warm up? The real reason going to higher temperature may be a problem is that this length scale becomes very short.
I see.
And when you go to warmer temperatures, this goes down, and also this goes down. So the range of scales, you would like your devices to be micron size, not nanometer size, right? And so if you want this to happen at a micron scale, you need temperatures to be not too high.
So LE is T squared, and LE times electron phonon will be 3/2.
Yeah.
Okay. Yeah.
So can I think about this geometric mean as a diffusion problem where one scale, the LE, is the range along which the momentum travels, and the other one gives me the average momentum of the Drude problem? So would this be?
Yeah, no, I think that's right. Must be. Yeah. Okay. Good. So let's so let's do this quickly, and then proceed to something something more relevant. As one signature of hydrodynamics, now there are many, and people invented many other manifestations of hydrodynamics, but this one I like particularly strongly, and you'll see why. Superballistic transport. How do we see that we're in a hydrodynamic regime? The idea is to take a slit, and the slit size should be in that sweet range that we convenient range that we identified, where hydrodynamic behavior should dominate, and so we should take it the right size and go to take temperature to be such that LEE is comparable to width of the slit or smaller, and then study transport. Now, what do you expect? Before we talk about that, let's talk about what you expect to see for free particles. For free particles, there is the famous Landauer assertion that slit through which particles are going freely will have finite resistance, even though each particle going through the slit does not dissipate at all. And the value for that resistance, more conveniently written as a conductance, and conductance will be E square over H times the number of conducting channels, which is how many times Fermi wavelength fits in the width of the slit, half wavelength fits in the slit, and that's the formula. And that formula can be, and also the relation to resistance can be understood in a quasi-classical picture very nicely by the Sharvin argument, who explained that finite resistance is actually not due to particles that make it through the slit, but due to particles that don't make it through the slit. And particles that electrons that have the velocities aimed the wrong way, they are back reflected, and if you work on what this back reflection translates in terms of dissipation, you find that finite resistance value, and 1 over r of that value is Landauer conductance. Sharvin also did the first experiment. He plunged a sharp metal tip into metal surface and observed that at low temperatures there is a ballistic behavior, more or less in agreement with that picture. Later, people developed this to a higher level and introduced slits with the width which is tunable by gates in the slit in a split gate geometry, like in gallium arsenide two-dimensional electron gases, where you put two gates on top with a gap in between, and then by applying voltage can open it and close. And you see that as you vary the width of the slit, which is basically the gate voltage in this picture, the conductance grows linearly with the width as predicted by Sharvin and Landauer formulas. And then every time one additional channel opens up, you see a step of E square H times 2 because of spin degeneracy. And so all of that works very nicely for free particles or at zero temperature. And then if you warm it up, particles will start colliding, and we expect a hydrodynamic behavior to happen. And if that happens, you can think about it and understand that you expect conductance to actually go up. And so the surprising observation here is that this ballistic conductance, prediction of ballistic conductance, the value that we get from a Landauer argument, Sharvin argument, does not give the maximal conductance that the system can have. Thank you. Conductance will be higher if particles start colliding. And that's really surprising, and interactions usually hinder conduction, not facilitate it. And here it's the other way, right? So the reason interactions help is that if you think about what individual electron is doing, in the presence of that hydrodynamic flow, it will be carried through, will be pulled into the slit by flow of other particles, and then it will collide with other particles, on a scale which is LEE, and as a result, its initial velocity, which may be pointing the wrong way, so that if it was a free particle, it would back reflect and wouldn't make it through the slit, becomes irrelevant. So the phase space for electrons that make it through the slit becomes wider because of collisions, and that explains why this Landauer-Sharvin bottleneck for getting into the slit, which ultimately determines the value of Sharvin resistance, why that is removed by introducing collisions. And if you do calculation, let's say using that type of an approach, solve classical hydrodynamics equations, you find that yes, indeed, conductance goes up, and the factor you gain is the order of the width of the slit divided by LEE, and so that's an interesting prediction. And in graphene, it's also very convenient, to test it, because at zero temperature you get ballistic behavior, and at finite temperature you get hydrodynamic behavior. So all you need to do is just make a slit and then study temperature dependence. And so that's what people did. Yep. Sorry.
The quantity we're talking about is the two-terminal conductance, or what?
I'm about to say that. So for experiment, the Manchester group made an array of slits, and they applied current through two terminals, source and drain, and then measured voltage drop on each slit individually by a pair of probes on the side. So it's a 4-probe measurement.
So it's a 4-probe measurement.
But I mean, it's a millipede, a centipede, or whatever probe measurement. For each slit, you have a 4-probe.
4-terminal. So in some sense, I could have looked at it from the 4-terminal perspective and say, if it was Galilean invariant, I would have infinite conductance, because electron-electron interaction doesn't dissipate it doesn't lead to momentum loss.
Next slide. Yeah. So we'll see where it builds up, right? So if you do it at zero temperature, you see that at zero temperature you get a pretty good agreement. This voltage measured on each slit agrees pretty well with Landauer and Sharvin, and that's just because that Sharvin resistance, Sharvin voltage drop builds on a scale of order of the size of the slit, and I think Shahal is going to talk more about it. They're actually measuring it now, right? So that voltage drops on a scale of order of the size of the slit, and then on a larger scale you see full voltage drop. Yeah. Good. So there is a good agreement with ballistic picture, and then if you turn on temperature, you see that resistance goes down and conductance goes up, and it goes down relative to the ballistic value, which is what we saw at 0 temperature, and there was a pretty good agreement with the model. And so that that proves that indeed interactions, when you go to hydrodynamic regime, A, you do enter hydrodynamic regime, and B, interactions do make conductance higher than ballistic value. All right.
I'm still puzzled by. Oh, not puzzled. I still would like to follow up on what I said before. So, if it's a four-terminal conductance, why should I think of it as a super ballistic? In some sense, I should think of it as smaller than infinity, because I have a breaking of Galilean invariance. So I would expect something that's small. What I mean to say is that I shouldn't have expected an integer. I shouldn't have expected the Sharvin result to hold anyway, because it's a four-terminal measurement.
Well, I mean, expected or not, but they see it, and the reason is, I mean, just wait for Shahal's talk. I think he's going to talk. The question is, where does the voltage drop? And the voltage does not drop in the probes; it drops on the junction. Yeah.
Practically two-terminal resistance with the actually measure, because they put a voltage, they put a current and measure a voltage on the two sides.
But they measure the voltage
on one side of a hole, and on another side.
Yeah. Different than
Okay.
current.
Can I mean, let's move on. So the thing I want to maybe do now, let me see what's happening.
May I just a quick thing?
Yeah.
Just trying to reconcile one thing. So your answer depends on the viscosity of the liquid, but not on thermal conductivity.
Not on.
Thermal conductivity as well. So I'm just trying to reconcile what Steve had, Boris and Anton. Why? Is that piece, which is 1 over k, is somehow small in some parameter range or not?
I mean, I don't know. There may be a thermal conductivity contribution, but there are also more serious problems with this approach that I'm not telling you about. I mean, for a qualitative picture, it's good enough, and then quantitative, let's do it. Let's discuss it tomorrow. Okay. Yeah.
So it's going to be different than where you're going to go. But can you ask about scattering, which is not temperature driven, but really interactions at 0 temperature, and think about this effect? So would you get collective mode enhancement of the conductance through a slit like that? Is it possible, or is it always working the opposite way?
Yeah, so people worked on it. I mean, there have been papers, trying to see what interactions do to at 0 temperature to ballistic transport, and at 0 order, find nothing. I mean, there was a lot of confusion, whether they enhance conductance or not. But then, at the end, it was established that this was about 15 years ago, 20 years ago.
I was not really referring to this, but thinking of what's the collective wave, right? This is in the limit where you have many wave vectors enter the slit. It's not a single chunk. So now you can think what the interaction does to this confinement of the wave function in the perpendicular direction, and whether this can explain some of the enhancements.
Yeah, so I haven't thought about it deeply, but I mean, Landau says that think about free quasi-particles and forget about interactions. And that's what experiment seems to be telling us also. I mean, that's all I have to say. Okay. So, right, maybe from here let's do, let me say this. If we want to understand the behavior in in this experiment, as well as in other experiments that probe hydrodynamics, as we already discussed here, we need to work not deep in the hydrodynamic limit, because extreme hydrodynamics does not happen. It doesn't happen because of this limitation, because of other limitations. We have to work at the length scales which are of order of the mean free path, and at the length scales of order of the mean free path, we'll see the crossover from ballistic behavior to hydrodynamic behavior, and that is a very interesting problem, as it turns out. For example, here, if you ask how conductance goes from Landauer value to this value, you can ask. Basically, it's a question about what happens if you ramp up temperature dependence, and that cannot be answered by solving Navier-Stokes equations alone. You have to have a more detailed approach that allows you to understand behavior, the crossover, the onset of the hydrodynamic regime, and there is analysis that we did, and I'm not going to explain the details, but kind of sketch the idea that predicts that in the crossover region, conductance is described by this formula that the conductance is equal to the sum of the ballistic conductance at zero temperature and the viscous conductance that you would predict from the Stokes equation, right? So there is this interesting addition rule for conductance. Ballistic and viscous just add up, and that describes very well the simulation results. Also, seems to be in a good agreement with the experiment, and that formula can be used to actually extract electron viscosity, and so I think. The moral of the discussion is that electrons collectively, by exchanging momentum, can squeeze through the slit easier than each of them would do so individually, with lower resistance and lower dissipation, and so doing it together helps. And then, actually, maybe before we proceed to that, let me just introduce a couple of things that will be useful later, tomorrow in particular, and also explain the idea of that calculation. So what you want to do, and what you want to think about is Boltzmann transport of quasi-particles, and that Boltzmann transport is described by Boltzmann kinetic equation written for particle distribution. And you are interested in linear response because you are calculating linear conductance. So we take that and linearize near equilibrium, and then when we linearize, we get a linearized transport operator where this term is the collision operator, which is a highly nonlinear thing that Joel was showing, but linearized about equilibrium distribution, and then it becomes an integral operator in momentum space, and that operator should go here, and then the electric field by which you're driving the system is there, and because I'm interested in delta F distribution linearly proportional to E, I can set this to an equilibrium value and not linearize this term, but just replace F by equilibrium value, and that's the linearized kinetic equation that people work with. And the type of response function that we need is a response to a spatially varying field, and just for generality, one can also add a time dependence. So I will say that my electric field is a spatial harmonic with wave number k and frequency omega, and look for solutions to that equation of this form. And then the last thing is that if temperatures are much smaller than Fermi energy, all the action is happening near the Fermi level, and because of that, I can linearize. Because of that, I can take this delta F in the form, df d epsilon, df equilibrium d epsilon times a sum of angular harmonics which describe the angular structure of your perturbation. If this is the Fermi level, this is the Fermi surface, then delta F for m equal 6 will have the structure, and for m equal 3 it will have that structure, and so forth, right? So you expand on angular harmonics, and then in this basis, your collision operator, because collision operator preserves cylindrical symmetry, it will so those circular harmonics will be eigenstates for collision operator with some eigenvalues. The eigenvalues are, maybe pretty non-trivial, and we'll discuss it tomorrow. But there are some eigenvalues, and you can just say that these eigenvalues are a genetic code of your scattering, of your different scattering processes. And they base some general rules, like for m equals 0 and m equals plus and minus 1, they must vanish because that's momentum and particle number conservation. But otherwise, they are non-zero, and they may have some interesting m dependence. So tomorrow, we'll see that in a two-dimensional Fermi liquid, there is an even-odd alternation, and even m correspond to higher relaxation rates than the odd m, and the ratio is going to be gigantic. But I mean, what I'm saying now is more general than that. If you just say that there are some eigenvalues, you can ask, let's compute a response function, and it's simple algebra in principle, but requires some care. And what you get in the end is pretty interesting. So if you take this electric field perpendicular to k, the wave vector, you get current. So the procedure is the following: you take this equation, invert transport operator, and write delta F as electric field times the inverse of the transport operator, and then use this delta F to compute current. And then this current proportional to electric field will define some conductivity, and this conductivity will usually have a non-trivial k dependence, and one can derive this very general formula. For conductivity in the form of a continued fraction. And in this continued fraction, so it looks like drew the formula essentially, but this gamma will be a function of k. And sorry, I forgot to say where k enters, and that's very important. So k enters through r, which is k square v square over 4. So there is this, there is this wonderful formula that says that there is take the set of gammas that you obtain somehow from collision integral, and then this formula will tell you what conductivity is, and that's it. And then with this non-local conductivity, you can solve any problem. And give me a problem, and using that conductivity, I'll solve it for you.
I'm not going to give you one, but just asking, if all the gammas are 0, don't you expect sigma to go like 1 over k? I mean, just a Landau damping? So this would be...
yeah, no, you get that, but I mean, you get that in the limit. Taking gamma to 0 in a continued fraction is delicate, but I mean, we can work out a simple example, and we'll see that you're exactly right.
No, I know it must come out.
Yeah, it will come out. It will come out. It will come out. I mean, we can do it right now, but I'm not sure we have enough time. But I mean, what I want to do instead is to connect with viscosity. But the idea is that the idea of solving all these problems is that you first determine, pick your favorite gammas, and then you compute non-local conductivity using that continued fraction, and then you have to. So, for example, for this problem, what you do is the following. Let me pull up the screen. Almost. Okay, and let's. Yeah. So. So for the slit problem, what you do is the following: you take this non-local relationship between current and field, and that's very general. You can write as a momentum space or some non-local relation position space, and then we have to set boundary conditions. But to set boundary conditions and treat them for real, is very complicated. So to do it, in this case, we invented and used the following trick. We replaced boundary conditions by momentum dissipation at the boundary. So we said that electric field will be a sum of an externally applied field that drives current minus some alpha times alpha that lives on the boundary and current at the boundary. And this is saying that at the boundary momentum is dissipated at the rate which I set in by hand, and it describes boundary on which particles relax their momentum, and then plug it in, and then you get an integral equation for g of x, and then solve it, and then take the limit alpha goes to infinity, so that the boundary becomes fully momentum relaxing, and that's how this calculation basically proceeds. Okay, and I mean, there are nice, interesting things that happen there if you actually look in the details, and probably there is some nice mathematics that we still have to discover. But the idea is just that you take this non-local conductivity and then combine it with this boundary condition that you cook up to force momentum to relax on this boundary, and then treat the problem in the plane. So replace boundary. The boundary will be nominally penetrable, but every time particle gets to the boundary, its momentum will relax at this rate. Okay, and that's how we are doing calculation for this problem, and as well as for other problems. How much time is there? Okay. Oh, good. So we're almost done. Let me just use this formula to show the relation with this Navier-Stokes equation way of calculating conductivity that was here earlier. If you now take that and say, let's go to the long wavelength limit. Go to the long wavelength limit, that means that R, which is k square v square over 4, goes to 0. Then I mean, nominally, this is k squared, this is k squared, all of these are k squared, so all these terms will go away, and we'll be left with conductivity, which is just drew the value and no k dependence. But now suppose that for one reason or another, gamma 1 momentum relaxation is small. So suppose that we are in a situation when this guy is small. Then, even though we're in the long wavelength limit, we need to keep next order term, and next order term in k will be this one. So here I will forget about all k squared terms here. Drop all these, drop all the levels of the continued fraction except the first one, and then here and then this will generate.
Leonid, in your case, gamma 1 is 0 exactly, no?
Yep. I'm about to say that. And this will be gamma 2. Right? And so then you see that what happens here is exactly the conductivity that you get if you invert this operator, and then this will be gamma 1, and then this eta is going to be this number, and then from that calculation you can actually read off the relation between viscosity and Fermi velocity and the relaxation rate for the elliptic harmonic, the m equal 2 harmonic relaxation rate, right? So and then in the limit you mentioned, if your momentum relaxation in the bulk simply doesn't happen, so forget about phonons. You can remove this gamma 1, and then you get conductivity that goes like 1 over k square. So that 1 over k square means that conductivity is a function of length scale, and current field relation depends on the length scale you're probing it, and so that's non-local conductivity in that limit. But actually, for these problems, the non-locality can take many other different forms, and more on that tomorrow. And let's see what else I was about to say here. Yeah, maybe you just ask questions, and I'll remember in a second. Any questions?
So, how do you formally distinguish here when you look for the response at given k and omega? How do you distinguish between transport limit and just screening, where electrons just screen electron field and electric field and don't flow anywhere? Is it in the boundary condition there, or where?
Even space charge.
Right. Yes.
Yeah. So I dropped space charge from the story, hoping someone will ask. Hoping no one will ask. But the way you thank you for the questions. So the way you put it in, is that you in this field you actually put in the space charge. So this should really be E external minus gradient of phi, and then this phi of x is the potential of the density buildup due to the distribution, due to our distribution function. So it will look something like that. And so that adds one more term to this equation and accounts for space charge effect. It turns out, however, that we are okay ignoring it, because one can do a simple transformation, which is a non-equilibrium version of going from chemical potential to electrochemical potential, and get rid of this term, and then this delta Fs will not be Landau quasi-particles distributions. That they'll be slightly modified. They'll be twiddled Landau particle distributions, and then everything else will stand. So this trick, I think, I learned personally from the old paper of late Jusek Levinson. But yeah, I'm sure it's been known to many other people. So yeah, maybe, okay, if any other questions? Yeah.
So cool question. So you began by introducing this outscaling Creighton Landau picture, T square epsilon square, by the phase space. So now, when you do this angular harmonic for the distribution function, it means that they decay formally with different rates, right? So is it just the same T square and then some m-dependent number, or there are some other miracles that all of a sudden?
There'll be lots of miracles. Wait for tomorrow. Yeah, there will be. And actually, Patrick, who knows all about, is sitting right next to you. So it's his achievement. So yeah. So maybe one more thing I will say before we close. If I take your suggestion, and in this formula forget about gamma 1, then I get conductivity which scales inversely with k square. And the coefficient here, as we discussed, is viscosity. And then if I take that, I can look at the slit problem. And then for the slit problem, I'll see that this predicts, if I set k of order 1 over w, the width of the slit, then this will predict that conductance of the slit will scale as w squared, and then viscosity is proportional to mean free path. So it will scale up to other numerical constants, will scale as w squared divided by the mean free path. And I can write it as, I can also write it as a ballistic conductance which scales linearly with w times w over LEE. Okay, so that's where the slit problem stands, but that's in a deep Hydro limit. To actually do it on a scale when w is of order LEE, you have to take the full account of that non-local conductivity and go from what Adi called skin effect. How do you call it?
I called it Landau damping, but it's the anomalous skin effect.
Anomalous skin effect, right? So it's an anomalous skin effect limit to that viscous limit and interpolate all the way in between. One nice way to do it would be to take gamma 1, to take all gammas greater than 1 be the same, right? And then gamma 1 be 0 because that's momentum conservation, and then conductivity is simply r over gamma 2 plus r over gamma 3, but because they're all the same, that's the same as sigma, right? So if all numbers in the continued fraction are the same, you can, from continued fraction, you can write down a self-consistent relation for conductivity, solve it, and then you will have a full k dependence, which will be something like, it's a quadratic equation, but
it will go from k squared to k.
Difficult to solve quadratic equation.
No, I think I'll be, yeah. After your talk, I'm energized. So it will be gamma 2 over gamma 2 square over 4 minus gamma 2 over 2, something like that. And then just to make it clear, this is k square v square over 4, and there is a plus, right? And so this will interpolate between the ballistic and viscous limit, and if you use that conductivity combined with this approach, you will get a solution to the slit problem. Okay, so I think, yeah.
The limit LEE is much larger than W.
Yeah. Yes. So that corresponds to k here being large. If k is large, we should.
Oh, it's saying W much louder than LE. Small k.
That's the strong interaction.
W, which means k is very small.
Weak interaction.
I think you need an inverse around the whole thing.
Yeah. It must be linear and k.
Yeah.
I told you that it's difficult to solve quadratic equation.
Oh, I'm sorry. I'm sorry. This is not sigma. This is gamma. I mean, this is correct, but this is gamma, and then this gamma should go in that formula, and then I think you'll be happy. It will be 1 over k. No, then it will be 1 over k at large k.
You can get this result by standard perturbation theory in the interaction stuff.
Yeah.
Ballistic.
Yeah. Yeah. No, I think that. Sorry. So this is the right way to do it. I mean, we have this continued.
Somebody did it. Yeah.
We have this continued fraction equation for gamma, and then if you write down gamma as a solution of quadratic equation, which is this one, and then plug it in, then everything will come out. Okay, I think we should. I mean, more questions? Yeah.
So is photon scattering quasi elastic in graphene? Is it true? As usual, because of the small sound velocity, la la la.
Yeah. Okay, so the relevant phonon scattering is quasi-elastic. I mean, there is some complication because the thermal phonon momentum is usually much larger than K Fermi because the Fermi surface is very small. But so most of thermal phonons have momentum much larger than K Fermi, but they don't contribute to momentum relaxation. They contribute to energy relaxation, but yeah.
Intermediate regime where momentum is relaxed, but energy is not relaxed is like a half hydrodynamic regime. Is there anything interesting in there? So momentum is not hydrodynamic, but energy is.
So I think this is what Andy McKinsey is going to talk about. Let's wait for his talk. I mean, he thinks that they're probing this regime. Andy is not here yet, right?
Isn't that's just ordinary diffusion equations? So I mean, I would call that hydrodynamic. But
Yeah.
What will be if you include higher gamma, like 3? Like with the second gamma, you achieved that the agent of ballistic hydrodynamic conductance, but with gamma 3?
Yeah, so for example, in this equation, all gammas are included, and it's exact. They include all of them, but only in this case when all of them are equal. I mean, you're asking what happens if gamma 3 dominates over gamma 2, or?
Just different.
Different. Okay, so that's tomorrow.
Okay.
Yeah. Ask something. Yeah.
Maybe easy or hard question, I don't know. But since you gave, this is going back a little bit to what was on your slide, since you gave the sort of Fermi level temperature scale numbers, I was wondering, do you have temperature scale roughly for when is this hydrodynamic window? Since you need or I guess you can say temperature or length scales either way, but since you need the length scale to be larger than LEE but smaller than this LE times the phonon square root. So for what temperatures is that a reasonable?
Yeah, so that's what Grisha asked implicitly. I think the story is that the higher the temperature, the better, but then the length scale becomes very small because both LEE and L electron phonon shrink with temperature, and so the room opens up, but it opens up on a very small scale. If we are limited by the scale, let's say we're building a device of a micron scale, then we want micron to be in that window, and we want that square root length scale to be larger than micron and electron scale to be smaller than micron. So then there'll be a trade-off for temperature. It cannot be too high, but also cannot be too low. There will be some temperature window that we can try to aim for. No, I mean, this is a really important question. I mean, all the discussions about it happen precisely about this point. Ask them, yeah.
Just quick question. If I replot this formula in terms of temperature, so temperature enters in your gamma, right? It's 1 over T squared or T squared.
Mm-hmm.
Is it non-monotonic function?
Of course, yeah. It will be okay.
No,
I think no. Here, I think it will be monotonic, and it will be going down with temperature, right? I think you maybe.
It depends on what you're plotting, but conductance would go up.
monotonic.
Yeah, sure. Conductance will go up, resistance will go down.
But when you showed the data, it looked non-monotonically. Is it something else beyond the picture that it's to do with an experiment? I mean, that experiment was a point contact. You showed that there is the strength and temperature dependence that looked like a monoid.
Oh,
went
okay,
down and up.
that one, yes. So,
Yes.
so that was because of phonons. Sure, we can get that if you reintroduce gamma 1 and make gamma 1 vary with temperature, so it becomes very large at large temperatures. Then you get this non-monotonic behavior.
Sorry, I'm kind of also getting back to my question about thermal conductivity, but how do you know? I mean, I can get non-monotonic temperature dependence also including a term in the resistance which is dependent on thermal conductivity because it scales differently with viscosity.
That term is going to be extremely suppressed.
Why? That's my question. So why? By which parameter?
No, we don't. See, I didn't claim anything about this up part because I mean, this model describes it, but I think there are many other ways to describe why at high temperatures resistance goes down why at high temperatures resistance goes up and conductance goes down. But for low temperatures, I think there's no other competing proposal for why increasing temperature from zero temperature you would go above the ballistic limit. So I think what goes at low temperature is a pretty clear signature of hydro, and then what goes at high temperatures, I think it's an interesting question, but still open.
I just wanted to know, what is the argument for the decay rate of the odd moments being relatively small? The odd harmonic?
Yeah, let's wait for tomorrow. It's the beginning of a long story. Will be very interesting, but now not enough time.
You were talking about how the electron phonon scattering rate is also temperature dependent. In that case, I guess it's more the phonon temperature than the electron temperature. And I guess in graphene, we know that we can separate the electronic temperature and the phonon temperature by just heating up the electrons. So we can actually have very different temperatures. I guess at this point, we're always talking about these temperatures being the same. Levitov heard all about the opportunities of separating these temperatures by, say, heating up the electrons.
Mm-hmm.
Kind of get stronger hydrodynamic effects.
Yeah. No, that's what people. So you see, okay, is Lawrence Molenkamp not here yet, right? Because this will be key for his talks. So in gallium arsenide, that's the most important thing, because in gallium arsenide, as it turns out, that nice interval where hydrodynamics would happen without any other tricks is too narrow and is not very conveniently placed. And because of that, people try to do just what you said, to warm up electrons by applying high current, and then make electron temperature higher than phonon temperature, and that will effectively make LEE shorter without changing electron phonon, or not too much changing electron phonon relaxation. So I think that he will talk about that.
Okay, so let's think.